Welcome back. Before we start this lecture, I just want to walk through with you a little bit of what we cover. We walked through the support vector regression in the last session. We covered both linear polynomial as well as the RBF kernel. It turns out the RBF, as usual, has performed the best, followed by linear, and finally polynomial. Polynomial actually performed the worst amongst the lot. Right. Before we end this so-called theoretical or the foundational section of SVM, I'd like to cover some of the advantages and disadvantages of SVM. The advantages of support vector machine are the following. It is very effective in high dimensional spaces. It often uses only a subset of training data. Sample data. Those are called support vectors in the actual decision function itself. The other advantage of SVM is that there are many different kernel functions that can be specified. Now that's really only limited to your imagination. Obviously it depends on your circumstances. You can always create new ones or apply those into the SVM itself. You have the linear, you have the polynomial, you have the RBF. We cover all three. There is also the sigmoid and also the custom function which you can define itself. There are some disadvantages of using SVM. The first thing is that you need to be aware of overfitting when the number of features is actually greater than the number of samples. The choice of kernel and regularization can have a major impact on the performance itself. The third disadvantage of using SVM is that there are no probability estimates. Now, the other thing that I just want to summarize is that the scikit-learn has three different implementation of SVM. You have the SGD classifier, you have the linear SVC, and then you have the SVC. Now, the SGD classifier, being stochastic gradient descent, can be computed more efficiently because you can actually do it out of core. It does provide out of core support, whereas the other two, such as the linear SVC as well SVC, does not. And unfortunately though, for SGD classifier, it doesn't provide or doesn't allow for kernel trick. Neither does the linear SVC. Only SVC provide the kernel trick itself. But there's just one thing to keep in mind. I've stressed this many times, is this: all of these requires feature scaling. Basically, when it comes to SVM, you must feature scale it. Now, SVM algorithms are not scale invariant, meaning it is highly dependent on the scale itself. So it is highly recommended that you scale your data. For example, scale each feature on the input vector or standardize it. Note that the same scaling must be applied to the test vector to obtain meaningful results. Now, to see the section on preprocessing, we already covered this in our previous section, but again, I highly recommend that you do read the scikit-learn excellent documentation. Where do you want to go from here? There are a lot of resources that I've listed down here, a couple of really good books as well. I mentioned in the previous videos that there is the libSVM and also linear as well. These are the actual creator of the support. Sorry, this library was created by these two professors in Taiwan. So feel free to actually dig through them because the Python implementation are based on both of these. So with that, I'm gonna leave you to it. Their convolution in Java does actually have some documentation and further explanation of SVM as well. But I think that suffice for now in terms of our foundation lectures on SVM. And I hope you've enjoyed it. I definitely have enjoyed bringing it to you. I look forward to seeing you in future videos. Thank you.